Okay, so this is officially the last class for in terms of the theory. So this should hopefully take about an hour, and then after this point, I'm pretty much finished the entire theory for the course. Okay, so after this point, will simply be review. So I intend to finish class hopefully by next Monday. So we're going to start, we're going to do some review for FM, and then next Monday I intend to finish the rest of the review. So hopefully we'll get everything done by Monday end of class, and then Wednesday you have off. There will be no class next Wednesday, so you can use that to study for your final exam. Okay? All right, so this is the last topic that we're going to be covering in the course. It's noise analysis of communication systems. So far we've only covered transmitting and receiving signals with no noise present. So we have to also consider the case where there is noise, which is inevitable, especially when you go out into the industry or in a practical setting. There's inevitably going to be noise in your communication system. So we have to talk about performance issues and exactly what kinds of things we're going to expect when you take a look at when you start introducing noise into your analysis for communication systems, all right? Okay, so in this last part of the course, what we're going to do is we're going to take a look at signal-to-noise ratios, or SNRs, for different communication configurations. All right, so what we're going to do specifically is we're only going to talk about amplitude modulation systems in terms of their performance. I decided to leave out FM mainly because I think it's quite an involved topic, and I think it's too hard to be talked about in this course. So when we talk about noise analysis, we're only going to cover amplitude modulation systems. So double sideband express carrier, single sideband express carrier, and amplitude modulation large carriers. So those three configurations we'll take a look at. We're not going to talk about FM in this course. So if you want, you can go ahead and learn about it on your own in the course textbook, but you're not required to know it for this course. You don't expect any questions on FM noise analysis for the final exam. This is just mainly for your own benefit. But I will not be covering that in this lecture. You're not responsible to know it for this course, but you can certainly learn about it on your own time in the textbook if you so desire. Okay, so what we're going to do first is we're going to talk about the baseband case. So this is the case where you are looking at the performance when you're not doing any signal transmission. You're not modulating to put it through a communications channel. So you're looking at it in terms of the raw signal by itself, the message by itself, without any transmission done on the actual signal. So this is the configuration we're going to compare to. So when we take a look at all the other modulation schemes like double sideband express carrier and single sideband express carrier and all that, we're going to compare those performances to the baseband case. And we would like it so that you want to be able to perform at least within some tolerance or pretty much exactly the same as the baseband case. Okay, so we're going to take a look at the baseband case first, and we're going to use this and compare with other modulation schemes. So the block diagram of the baseband case is pretty much shown here, right? So you have your input message and you have some transmitter. So it may not be modulation. It may just be through just through maybe a wire or so. But basically, there's no modulation involved. So basically, your channel or whatever you're transmitting through has low pass characteristics. Okay, so put it through a transmitter and then you put it through your channel, and then on top of that, inside your channel, there may be noise that could be added on top. So what we've seen previously is that we assume that there's no noise. So you put it through your transmitter, put it through your channel, and then you receive the same thing as what you get on the transmitter side. But there's no noise that's added on top. So we've been dealing with that pretty much throughout the entire course. But we have to talk about noise now because that is what you're going to see in practice. Okay? So when you add noise on top, obviously when you get the received signal, it's not going to be the same as the original signal because you've got all these noisy components that are added on top of the original one. So the received signal is obviously not going to look the same as your original one. So you have to figure out ways to mitigate that or figure out what to do to be able to retrieve your original signal as best as possible, trying to ignore as much noise as you can. Okay, so here's some basic notation here that we'll be using throughout this analysis. So the inputs and the outputs and the notation for this system are the following. So your input, which is just the message, which we'll call MFT, it's a time domain varying signal, okay? And then when you put it through your transmitter and then you put it through your channel, and then you're going to be able to, but you will have some noise that is added on top. This noise signal is called N of T. It's a noise waveform that is time varying just as much as your message signal, okay? And then S sub I and N sub I are the signal and noise power right before the receiver, pretty much inside the channel or right before the receiver end. So this is the input, signal, and noise power, okay? And then the output of this receiver, which we'll call S of 0T and N of 0T, those are the output message and noise signal that is at the receiver end. So you've got your message signal coming in, outside on the receiver end, you're going to have a different waveform because of noise that is contaminating your signal. So those are going to be separated. Those can be represented as two different signals. One, you can represent, theoretically, the input should equal the output. So, the input should equal, S of 0, and then you can extract out the noise and represent that as a separate signal by itself. So then you have S of 0 and N of 0, which are capital, and then that represents the signal and noise power at the receiver end. So what we want to do is we want to figure out what the signal to noise ratio is. So you have to figure out what the output signal power is from output of the receiver, as well as the noise output power. And then the ratio is just simply dividing them both, and you'll get some numerical measure that tells you how good of a system you have. So the bigger the SNR, the more robust it is against the noise, or it will ignore the noise as much as possible in comparison to a system with low SNR. So we're going to make the following assumptions throughout this analysis, okay? So there are 4 things that we're going to assume in this particular case. The first case is that we assume that the message has 0 mean. So this means that it is symmetric across the horizontal axis. So if you were to find the average value from one point to another, that average should be 0. So it's basically a symmetric wave that is oscillating around the horizontal axis. Okay. Also, the modulators, throughout the analysis, we're not using any modulators here, but when you're taking a look at double sideband suppressed carrier and all that, those modulators may have some sort of uniformly distributed phase. So it's a random variable, a uniformly distributed random variable that has some value between 0 and 2 pi. In this case, there's no modulation, but for later analyses, there will be some modulation involved. Oh, sorry. Also, the noise input is assumed to be an additive white Gaussian noise model. So we covered what an AWGN model was in the previous class. We're going to use that model that represents noise in our analyses here in this part of the course. Also, at the very end, the receiver, usually, at the very end, you usually have a low-pass filter, not only because, especially when you're taking a look at double sideband suppressed carrier and all that, you usually have a low-pass filter that gets rid of all the sideband components and you're left with the baseband. You also use a low-pass filter to get rid of as much noise as possible because the AWGN model corrupts every single frequency component by some constant amplitude. So if you put a low-pass filter, you're pretty much removing all the noise, but at the same time you're restricting it so that you're getting as much of the original message as possible, even though there's going to be some noise contaminants within the bandwidth of your signal. Okay? Also, what we're going to do for notational purposes is we're going to let the noise power inside the channel or before the receiver and outside of the receiver to be sigma I squared and sigma O squared. So that's just your standard notation. So you can represent it as n sub I or sigma I squared. One of those two will be perfectly fine, and n sub 0 or sigma 0 squared. So one of those will, you can use one of those for the input noise power and the output noise power. Whichever one of those you're most comfortable with, you're certainly more welcome to use. But in this case, we're going to use sigmas because those are what are traditionally used when you take a look at analyses of this type. Okay, so the baseband case. So let the input signal inside the channel be yi of t. Okay, so yi of t is going to be this input right before, actually let me see here. Yeah, so, sorry, the input signal inside the channel. So as soon as the input comes into the channel, you're going to add some noise. So right at the output over here, right before the receiver, you're going to have your channel, you're going to have your message with your noise added on top, which is what this is, all right? And then as soon as you put a low-pass filter on the output of the receiver, you'll have the original message, which is what you want, right? Because you have a low-pass filter that spans the bandwidth of the original message, but then you're going to have a low-passed version of your noise signal. Because remember, your noise basically spans the entire frequency spectrum. So if you put a low-pass filter on your noise, you're filtering out everything else except for the components that are within the span of the bandwidth of your message, which is why we call it as n sub LP. So it's the low-pass version of your noise signal. Okay? If you recall from the previous lecture, if you put a low-pass filter on an AWGN noise random process, if you wanted to determine what the power was, you remember it's just simply n sub 0b, where n sub 0 is some experimentally found constant, which is usually 10 to the minus 10. But if you remember from the previous class, if you put a low-pass filter on your AWGN noise model, if you find what the total power is, it's simply n sub 0b, just from the previous class. All right? So if you want to calculate the signal to noise ratio, it's very simple. All you have to do is just take your signal power divided by your noise power. You're taking a look at the output of the receiver, and that's simply what your signal to noise ratio would be. So the output, the signal to noise ratio, which we'll call gamma, is just the signal power, the output signal power divided by the output noise power, and we determine this to be n sub 0b for the output. And then whatever the output signal power is, you're going to let that be s of 0, and that is our benchmark. So the signal-to-noise ratio is usually in watts per watt, and sometimes you express it in decibels. So if you want to express the signal-to-noise ratio in decibels, you just take 10 to the log 10 of whatever that volume is at the top, and this is represented as decibels. When you're taking a look at power, you usually use 10 log 10. If you're taking a look at volts per volt or amps per amp, if you're taking a look at normal decibels for voltage or amperage, you take 20 log 10. But in power, you do 10 to the log 10 because the quantity is squared, so you have to divide by 2 to compensate for that. So the above result will be our benchmark when comparing with other signal-to-noise ratios for different communication systems configurations. So what we're going to do now is there are 6 steps that we're going to follow to evaluate the signal-to-noise ratio. And these are the 6 steps you'd follow if you were to have an exam question of this particular type. So if you just memorize these 6 steps, you'll pretty much be able to solve any type of question that is something that is similar to this very easily. So these are the 6 steps. So when you have a communication system that is amplitude modulated, we're assuming that the noise is additive. That's why it's called an additive white Gaussian noise model, because you're taking your message and you're adding noise on top of what you already have. So theoretically, because the noise is additive, you should be able to theoretically separate the signal and its noise signal, as 2 separate entities. But that's, that's something for later. So here are the steps if you want to analyze, do noise analysis for amplitude modulation systems. So when you have your block diagram of your communication system, the first thing obviously you have to do is you have to take a look at each node in your block diagram and determine what the actual signal at that particular node is in time domain. All right, so that's pretty much the standard thing that you have to do. But what's really important is basically steps 2 to 6. So what you need to do is you have to figure out what the input signal is, into the channel or into the receiver. You have to figure out what that is, right, and express it in terms of its signal and noise components. Once you figure those out, you figure out what the signal power is and the noise power is. Okay, then you do the same thing, but for the output signal, the output of the receiver, and then you figure out what the output signal and noise power is of the receiver. So you're going to have 2 time domain signals: the input that's going into the receiver and the output that's coming out of the receiver. And then when you calculate the output signal and noise power, you want to relate it in terms of the input. So express the output signal and noise power in terms of whatever the inputs were. And then using what you calculated at the top for 5, you determine what the signal-to-noise ratio is, and then you compare that with the baseband case. Okay, so these are pretty high-level steps, but it would be nice to actually go through some examples, which I'll go through right now. Okay. Okay, so we're going to talk about our first configuration, which is the double sideband suppressed carrier configuration. So this is a block diagram on the right here that pretty much shows you how exactly the double sideband suppressed carrier configuration works, going from transmission to receiving. Okay, so just a quick overview of what this block diagram does. You have your original message signal, right, and then you modulate by cosine wave. So this is double sideband suppressed carrier. We have a root 2 here because you'll see that later on this will actually make the math a lot easier to use, so to actually perform. So we put a root 2 here as a scaling factor to make the math a little easier to analyze. So m of t times cos of t, so you have your double sideband suppressed carrier here, right? So this is what is being transmitted, so that's your modulation scheme. And then you add noise on top. So when you're transmitting through the channel, there's going to be some noise that corrupts your actual modulated signal. And then this bandpass filter here, the reason why this is here is because, remember, your noise signal corrupts every single frequency component, possible. So this bandpass filter allows you to be able to get, to isolate out to your, so it's used because you want to span it so that it's within the bandwidth of your double sideband suppressed carrier signal, because when you modulate, you're shifting it over to wherever the carrier frequency is. That's the central carrier frequency. And then it spans between -b to +b in hertz, or -2 pi b to 2 pi b in radians per second. So it spans 4 pi b. Okay? So the reason why you have a bandpass filter there is because you want to eliminate all the noisy contributions except for, you want to be able to extract out what the modulated signal is, but at the same time there's going to be some noise that corrupts within the same bandwidth as your DSB-SC signal. So it tries to retain the message components as much as possible, which is modulated, but at the same time, it removes all the noisy components, but still there's going to be some noisy components that actually corrupt your message signal, which is modulated. And then at the receiver end, of course, in standard, you just multiply your signal by cos again, standard demodulation. And then you have a baseband filter, which is a low-pass filter that gets rid of all of the other sidebands and just gets the actual message signal by itself. And then it also tries to remove as much noise as possible. Okay, so we're going to let S of t be the modulated signal. So right at the output of the transmitter, but right before the channel, we're going to let that be S of t. And then X of T is right after the channel, so over here. So it's just, you know, the modulated signal with noise added. And then there's a bandpass filter that filters out as much noise as possible, but remember, you're retaining the message that is modulated, but at the same time you're moving out as much noise as possible. So if you remember what a double sideband suppressed carrier signal looks like, you remember you're centered at your carrier frequency, and it goes plus minus B or plus minus 2 pi B, depending on which domain you're looking at. So it's the bandwidth is either 2B or 4 pi B. And then the baseband filter just is a low-pass filter that removes everything except for your message signal, and then there might be noise on top. And then each modulator has a factor of √2 to make the math a little simpler, and we're going to go through each of the steps now. So here's the first step. The first step, okay, is to figure out what the output is right at the transmitter. So all you're doing is you're just taking your message, and then you're multiplying by your cosine wave, which is your carrier. There's also a √2 factor as well, and that's what we get, which is totally fine. The next step is to go through the channel, add your noise, which is fine. So if this point here is S of T, you add your noise, and that output is X of T, which is pretty much here. So the only difference between the transmitter or the channel is that you're just adding your noise signal on top, which is in the time domain. All right? The next step is you analyze what's going on here. So this is the input signal before you get into the receiver. So that's what we're trying to analyze. So this signal Y of T is basically the result of taking your signal X and just putting it through a bandpass filter, right? So if you put your signal through a bandpass filter, remember that the bandpass filter is designed so that the double sideband suppressed carrier component will be still maintained. So if you put a bandpass filter through this signal here, so you're still going to get this component because this is going to be centered at omega C, and then the message signal is a bandwidth of 2B. So when you put a bandpass filter, this is still the same. But if you remember from the previous class, if you have a bandpass random process, if you put it through a bandpass filter, it splits up into quadrature components. So N of T, when you put it through a bandpass filter, it gets split up into these two things. So you have NC of T cos and NS of, sorry, this should be NS of T sine, right? Where this is simply modulated by cosine wave applied with a low-pass filter, and this is modulated by sine wave applied with a low-pass filter. So this should be NS of T. It corrects that before I post it online. So this first signal component here modulates the message, and it's centered at either omega C or FC. So because the bandwidth of your bandpass filter spans the modulated message, if this, this has no effect. This should pass through the bandpass filter, no problem. But then these last two components are what happens when you put a bandpass random process. Sorry, if you put a random process through a bandpass filter, so it splits up into two quadrature components, NC of T, and NS of T, right? Because the noise profile exists over all frequencies. Okay, so the next step is to calculate the input power and the noise power. So how you calculate the signal power is very simple. All you have to do is you just have to find the expected value of your signal squared. When you're trying to find the average value squared, the mean squared value. That's how you'd find the power in this case. So remember that we split this up into, so this is the signal component, this is the noise component. So if you want to figure out what the input signal power is, you just find whatever the signal power for this would be. And that's what's going on here. So you take this value, you square it, so √2 squared becomes 2, right? And then mt becomes m squared, and cos becomes cos squared of t, all right? And then if you remember, cos squared of x is a half times 1 plus cos 2 of x, and that's what's going on here. So the half and the 2's cancel, and then this becomes 1 plus cos 2, and then x would be omega ct here, right? And then if you remember, we're combining two things for the expected value, so there's linearity, so what we can do is we can expand this out, and then you can actually split up the average calculation into separate ones, right? And then what's going on here is that this second term, it evaluates to 0 because we assume that the average value of your message is 0. So if we're gonna integrate over a period, the average value between a period should go to 0. So the second term goes to 0, so all you're left with is this guy here, and this is simply the input power of your message. So what this is telling us here is that the input signal power that is going in before the receiver, it's simply whatever the message power would have been before you transmitted your signal over through the communication channel. So that's the input signal power. It's just the message power by itself. Okay, now we're going to do the noise. Okay, so if you want to do the noise, it's actually quite simple. Either you have the autocorrelation function and you substitute your time lag to be equal to 0, or in this case, if you have the power spectral density, you simply find the total area that's bounded under the curve. All right, so Okay, so remember this is our input signal power, and remember it was the AWGN noise model, but with a bandpass filter applied to it. So this output would simply be this. Remember the AWGN noise model was a flat line over all frequencies. So if you put a bandpass filter, this is exactly what you get, where everything is 0 except for centered at omega C or FC, whichever notation that you have, and then it spans, the bandwidth is either 2B or 4 pi B. So this is what the bandpass result will look like. If you want to figure out what the total power is, you just simply find the total area. So it's just basically width times height of this rectangle plus width times height of this rectangle. And there's two ways you can do it. The first way would be if you want to do it in terms of omega, you have to make sure there's a 1 over 2 pi here. So let's do it in terms of omega first. So you have 1 over 2 pi, and then this quantity here is just width times height. So the height is n over 2, n0 over 2, and then the width is 4 pi b. So that is this square over here. And then the next one is pretty much the same thing, right? It's just this square that's shifted over to omega c instead of minus, so it's still the same quantity. If you add these both up, you're going to get n0 4 pi b, and then when you divide by 2 pi, the pi's cancel, 4 divided by 2 becomes 2, and then you get this, okay? If you want to do it in terms of frequency, it's exactly the same thing. You don't have a 1 over 2 pi here, but you're going in terms of hertz. So the width here is 2b, the height is n0 over 2, and that's what we get here. So you have one rectangle, the width is 2b, the height is n0 over 2, you have another one, which is the same thing. You add them up. So basically what happens is that the 2's cancel, and when you add them both up, you get 2 n0b as well. So it doesn't matter which domain you're looking at. The fact is that you get your power to be 2 of n0b. So that would be the input noise power that is coming into the receiver, before you actually do the low-pass filtering. Okay, so this is the next step, step 4. So we did the first step. We figured out, what each of these components are. You put it through your bandpass filter. You figured out what the input and the input signal and input noise power would be. Now what we're going to do is we're going to demodulate. So you multiply by √2 cos, and then you put it through a low-pass filter. Okay, so that is what the output signal will be. So you take your input message, which is coming in, that is modulated and bandpass filtered to get rid of as much noise as possible. Multiply by cosine, so √2 cos, and then once you're done, you put it through a bandpass filter. So remember, when in a bandpass filter and frequency, you're multiplying two things together. It's convolution and time domain. So that's what's going on here. So I'm going to substitute yi of t, and that's what's going on here. So if you remember, yi of t was this signal over here. So you take this signal, and then you substitute it into this expression, and this is the expression that you get. So remember, y of t was √2 m of t cos, and then nc of t cos, and then ns of t sine. And that's what's happening here when you expand this. So the √2's and the √2's become 2, m of t, and then you have cos squared, right? And then this follows because the √2 carries over when you substitute it with yi of t. So this is what's going on here. And then you go ahead and apply a low-pass filter. So we can do a couple of things here. Firstly, what you can do is you can change cos squared to be 1 plus cos 2x over 2. We'll talk about that later. But what's important is that I can change this. So if you remember, sine of 2 theta was 2 cosine. So if I divide both sides by 2, that's what I get. So cos and sine is equal to a half sine 2. So I replace this with half sine 2. And then what will happen is that I'll have √2 divided by 2. So that's the same thing as 1 over √2 when you actually rationalize the denominator. So √2 divided by 2 is the same thing as 1 over √2, and that's what I get over here. And then what I'm doing here is I'm going to factor out a cosine squared omega ct. So we have two of these that have the same, there's a factor of those, they share the same factor. So I factor out a cosine squared. I can also factor out a 2 as well. So when I factor out a 2, this becomes m of t, not 2m of t. And then I have to divide by 2 for here, so this becomes 1 over √2 as well. So when you substitute, cos and sine into here, you make this half sine 2, and then you do some factoring, this is what we get. And then when you put this through a low-pass filter, what's going to happen is that this term will go away, and then you have to express this as well, which we'll take a look at on the next slide. So this is what we have so far, right? So we changed cos squared into 1 plus, 2, cos 2 omega ct divided by 2. So then the 2's cancel, and then this is what you get. Right, so this stays the same, and we're just expressing this in terms of 1 plus cos 2 over 2. So once you apply the low-pass filter, what's going to happen is that this term goes away, and this term goes away, so we're left with just the one on the left side. So once you apply your low-pass filter, this is the output signal that you get. So basically what this is telling us here is that if you have additive white Gaussian noise, the output message that you should get is the message signal as well as the it's basically your noise that is modulated by coast with a low pass filter applied to it, and it's scaled by 1 over root 2. So this here is your signal component, and this here would be your noise component. So now what we have to do next is we have to figure out what the signal to noise ratio is using the output, right? So here's the next step. So first, what you have to do is you have to figure out what the what the signal power would be. So basically, what's happening here is this is your signal, and this is your output signal, which is just your message, and this is the noise signal of the output. So you just have to find the power of each of them separately. So if you want to figure out what the output signal power is, you just take your message signal. If we figure out what the power is, it's just the mean squared average value. In this case, it's pretty much the same as whatever the message is from before. If you want to figure out what the output noise power is, you just basically take the expected value of this quantity squared. So 1 over root 2 of this squared. When you do that, this becomes 1 over 2, and this becomes this squared. And then you can take the half and bring it on the outside. This is what you get. And then this actually, if you remember from the previous class, if you found the power of the cosine quadrature component or the sine quadrature component or the output, it's basically all going to be the same quantity. So you can actually just replace this with the input signal power, which is just 2n0b, and then when you divide it by 2, you get n0b. Okay, so the last part is due to the fact that you have this equality here. So if you find the power of the the quadrature components, it's the same thing as the output of your bandpass filter, and that's simply 2n0b. You divide that by 2, the 2's cancel, and then you get n0b. So if you want to figure out what the signal to noise ratio is, it's just Sm divided by n0b. Okay, so that's pretty much the same thing as what you expect for baseband case. So the SNR for a DSB-SC system is the same as a baseband system. So basically it's the same as if you weren't to do any transmission to begin with, which is actually nice. So if you add a transmission scheme into the mix, you would expect that the signal to noise ratio is pretty much the same before you even did any modulation, which is very reassuring. Okay, so that's your double sideband suppressed carrier system. What we're going to do next is we're going to take a look at single sideband. So let's take a look at single sideband. We'll take a break, and then we'll do the last configuration, which is amplitude modulation, and then take another break, and then we'll do the tutorial. Well, one of the tutorials anyway. Okay, so we're going to take a look at single sideband suppressed carrier. So what we're going to do is we're only going to concentrate on just one sideband for now. So let's choose the lower sideband arbitrarily. You can actually repeat the analysis and take a look at the upper sideband, and you're going to see that no matter which sideband you choose, it'll actually give you the same power configuration. So I'll let you do that on your own, but I'm just going to choose the lower sideband for now, and then you can verify that you get the same results if you actually choose the upper sideband instead. Okay, so this is what the single sideband configuration looks like. All right, so you have your message signal that's coming in, and then these modulators actually have a 2 instead of a root 2 to make the math a little easier. So you first are modulating with the double sideband suppressed carrier, and then you have a bandpass filter so that you only filter, so you're filtering out everything except for the sideband that you want. In this case, we want to have a, let me see here, SSB. Yeah, so it produces, yeah, so you have your bandpass filter to extract out the lower sideband, okay? And then you transmit the lower sideband through your communication channel. And then this here is a pre-processing filter because you want to make sure that you eliminate as much noise as you can, but then you're limited to just whatever the bandwidth of each of the sidebands are, because obviously you want to be able to receive the message. But at the same time, if you have noise that corrupts every single frequency component, even though you have your bandpass filter that's centered around where your sidebands are, you're still going to have the noise that will leak into the the valid bandwidth of your bandpass filter. So this is mainly here to eliminate as much noise as possible. Okay, so this is your channel, and then you do the receiving. So with single sideband, right, what you can do is you can basically use standard. This is coherent demodulation, so you use a cosine wave and then use a baseband filter. So you can use a low pass filter as well to be able to extract out the original message. So this is just your standard single sideband configuration using coherent detection. Okay, so this is the same notation as before. So S of t, which is right over here, that's your modulated signal. X of t, which is going to be the signal inside the channel once you add noise to it. And then this single sideband filter produces the lower sideband portion, so it removes the upper sideband. And then this bandpass filter is centered around where the lower sideband is, but it removes as much noise as possible, but you still have noise that leaks in within the valid bandwidth of your sidebands. And then for the lower sideband, remember, it's the lower half, so it spans from your carrier frequency, so it's going to go from the left to the center, so from Fc minus B to B, or in this case for omega C, you're going from omega C minus 2 pi B to omega C. Okay, and then the modulators have a gain of 2 to make the math simpler. Okay, so let's go through the steps again. Very, very simple. So the first step is to figure out what the modulated signal would be. So it's at this point over here. So actually not this point, it's actually at this point over here, right? So this is right before you get into the channel. So you want to produce the lower sideband, right? So it's basically M of T cos, and then this is a mistake actually. This should be minus, but it actually doesn't matter because what's happening here, if it depends if it's, the only difference between lower sideband and upper sideband is a sign. So this would be minus for lower sideband and plus for upper sideband. So you'll actually see that it doesn't matter what the sign is, you'll still get the same results, but that's a little mistake that I'll have to fix for later. So this is your lower sideband signal, and then when you push it through your channel, you're going to have your noise signal that's added on top of this. So remember, this is your lower sideband signal, so this M of HT is your Hilbert transform, and then you add your noise signal on top of the single sideband. So that's what happens when you're doing single sideband transmission. So remember that MH of T is a Hilbert transform version of your message signal, so it's basically all components are shifted in terms of phase by 90 degrees. So the next step is to put this signal here, at the channel through your bandpass filter. All right. So remember, so you have this signal here. So the first two terms are basically your input signal. So they're centered at omega c, and they span the same bandwidth as your bandpass filter. So naturally, these two terms are going to come through your bandpass filter. But if you remember from the previous lecture, if you have a random process and if you put it through a bandpass filter, it splits up into two quadrature components, as we talked about before. So these, so this would be the noise components when you pass it through your bandpass filter. So the next step will be to calculate the signal and noise input power. So the input power is very simple. So what's going to happen is that you have to calculate the power of this term, which is your double sideband sparse carrier, and then this term, which is your Hilbert transform version multiplied by sine. So we're going to calculate both of these by themselves. So that would be the input signal power. So what's going to happen here is that if you take a look at cosine squared, right? What's going to happen is so this is actually a little bit of a mistake here. So so what's going to happen? So when you have M of T cos, it splits up to a half, and then 1 plus cos 2 omega ct. So that's the first part. The second part, when you have sine squared, it's actually 1/2 minus 1/2 cos 2 omega ct. So this should be a cos and this should be a minus, but it doesn't matter because these terms will actually cancel out. Because remember that when you are finding because we're assuming that the average value is 0, and then when you're putting it through cosine and sine, that average value becomes 0. So these actually cancel out. So when these cancel, what you're left with is just this term and this term. And what's happening, you can think about it where because what you're doing is you're taking your signal and you're doing a Hilbert transform. So all you're doing is you're just phase shifting every single component by 90 degrees. So that actually doesn't change the amplitude. So if you find the power of a Hilbert transform message, it's just simply the power of the message itself. So in that case, you're going to have a half plus a half because these two are equal. It can, it adds up to 1, and then this is just simply the power of your message by itself. So when you're doing single sideband modulation, the input power is simply the message itself. And this is what I talked about here. So why is the Hilbert transform power the same as the input message? It's because phase shifting doesn't affect the power, and the magnitude components stay the same. All you're doing is doing the phase shifting. And there is a theorem which is called Parsifal's theorem, where if you want to figure out what the total power of your signal is, it directly relates to finding the total area of your Fourier transform in frequency domain. So if you actually don't modify the magnitude components, then the power should pretty much stay the same. So because this is the case, the input signal power that you get is simply whatever the power of the message is when you're taking a look at a single sideband. Okay, so if you want to figure out what the noise power is, it's very simple. So you have your AWGN noise model, you're putting it through a bandpass filter where the bandwidth is B, not 2B. Then this is what's happening here. So this is what the result is when you put it through your bandpass filter, and if you want to figure out what the total noise power is just the area bounded under the curve. So you just find the area of this box plus the area of this box. So if you want to do it in terms of omega, it's very easy. You have 1 over 2 pi, and then the width here is 2 pi b. The height is n0 over 2. You have the same box on the other side, so you have twice these components. You add them up, you'll get n0 2 pi b. The 2 pi's cancel, then you get n0b. And then you can do the same thing in terms of frequency. So the width here is b, the height is n0 over 2. You have 2 of them, and when you add them up, you get n0b. So it doesn't matter which domain you're looking at, you're going to still get the same result. So, okay, so we have a couple more steps. We'll take a break, and then we'll do amplitude modulation after the break. Okay, so this is step 4. What's happening here is that you're going to put it through a modulator or a demodulator, put it through a low-pass filter, and see what the output signal looks like. Okay, so The output signal is simply taking your input signal, which is YIFT. You're going to multiply by your modulation, which is 2 cos, apply a low-pass filter to it, and see what the result looks like. Okay, so your input is Y, and then you're multiplying by 2 cos, which is what is over here, and then you perform your filtering with your low-pass filter. And then we can expand this out, because you know YIFT is going to be, so you have M of T cos and MH of T sine, and then you're multiplying it by, let's see here, 2 cos, which is what's going on over here. And then you'll have NC of cos and NS of sine. So that multiplied by 2 cos gives you this. Okay? And then what's going to happen here is that we see that we have some common factors. So the first and the third terms have a common cos squared term. So we can factor that out. And then we have M of T and NC of T, which forms this part. And then cos and sine have a common factor. So when you use those and you factor out with the 2, you get M of H and N of S as being common terms as well. So we know that 2 cos sine is simply sine of 2, and cos squared is a half times 1 plus cos 2. So when you do those substitutions, this is what we get over here. So this becomes 1 plus cos 2 omega CT, and when you multiply this through, that becomes the first 2 terms here, and 2 cos sine becomes sine of 2, and this is what you get. So when you finally put it through your low-pass filter, the third term goes away, the second term goes away, and then you're left with just the first term by itself, which is what we have over here. Okay, so this would be our signal component, and this would be our noise component. So what you have to do now is you just simply find what the output signal power is and the output noise power is. So the output signal power is just simply the power of this guy over here, and the noise power would simply be this over here. So that's the next step. Okay, so you figure out what the message power, so you figure out what the output signal power is, which is just simply the power of this component over here, which is just your message. And then you take a look at what this power would be over here. If you remember from the previous, couple of slides, if you figure out what the noise power is for the cosine quadratic component, it's simply whatever the output of the bandpass filter would be, which is just N0B. So if you finally took the ratio of these, it's just SM over N0B, which also matches up with the baseband case as well. So therefore, the SNR for a single sideband suppressed carrier system is the same as a baseband system. So it's actually looking pretty good so far. So your double sideband suppressed carrier configuration has the same SNR as the baseband, and the single sideband suppressed carrier system has the same SNR as the baseband as well. So I just did it for the lower sideband. If you wanted to do it for the upper sideband, it's exactly the same thing. It's just your bandpass filters would be moved towards the upper portion rather than the lower portion. But it doesn't matter, because if you actually go through and actually do the derivation, you'll actually get the same SNR. Okay, so we're going to take a break here. We'll come back in about maybe 10 minutes or so, and then I'll finish this up, and then I'll take another break, and then we'll actually do the tutorial. All right? So we'll come back in about 10 minutes.